Now we have talked about several extensions to the Black-Scholes Merton model. We have talked about 5 different variations of these different types of extensions to the Black-Scholes Merton model. Now, I haven't really gone into a lot of details to analyze and discuss these models for a number of reasons. Number one, they are relatively complex, so a full description of each of them takes a lot of time. So in the interest of time in this course, that's probably not worth it to go into a lot of details. Number two, there's actually pros and cons of using those model because of their complexity. A lot of the time you have to go into you know complex numerical implementation to be able to use those model effectively. And then the consideration becomes, how well you can do the numerical approach to, there are a lot of numerical errors in it as well. You have to handle the numerical aspect of that more precisely for you to be able to implement that model correctly. And then whether you've gained any advantage over using Black-Scholes depends very critically on how well you can actually implement those models numerically. If you implement it well and very efficient, you use very efficient procedures, then you will actually get something better than using Black-Scholes. But if the numerical implementation is relatively poorly done, then you actually not having any step forward than using Black-Scholes. You actually, it's actually not as good if you would just stay with the relative simplicity of the Black-Scholes formulation there. The other thing is that the for each of them, which model is the one to use. We've talked about 5, but for a given situation, you may need to select. If you were to move away from the Black-Scholes, you will have to select, which one to use out of those 5 different ones, right? There are many others as well. So not just the 5 we introduced, but there are quite a number of different ones. But that choice really depends on the actual situation. So what kind of options you're looking at, and the characteristic of the option itself, the complexity of the option itself, determines which model may be a better choice for that particular circumstance. So in order to discuss which one should be applied, then we really have to look at it from the perspective of the options. So that's why I haven't really spent a whole lot of time into the details of those different extensions or alternatives to the Black-Scholes approach. So the other aspect of that is that no matter which choice we make, we have to, it's very critical for us to be able to calculate or to calibrate parameters. And basically for all those different extensions, we would have to go through some sort of a optimization approach to calibrate the parameters that are required by the model. Typically, you will use the observed option prices, and then you have this price being produced by the model. Then based on a particular set of assumed parameter value, then you use this some sort of minimization routine to minimize the cost function here. Here it is a squared cost function here. So basically we're minimizing mean square error, and by minimizing that, it will give us a set of optimal set of parameters that provide the value for the model, which minimize the average square here. So then to do this, it's important to select some sort of a convergence threshold, and so to allow us to stop at some point so that we can call it a victory and then find the optimized parameter values. And so the stability of this minimization program is very important. And if the surface that you need to minimize is actually relatively flat, you may encounter issues to be able to successfully implement this minimization of error to select the required parameter value here. So it's actually quite tricky depending on the functions that you have that you needed to minimize here. So it depends on the shape of your cost function. Since the objective function may have a complex shape, it may not guarantee that you will have a global minimum. So you may have to accept that you reach a local minimum rather than a global minimum. So the parameter estimated is based on a local minimum. And the more complex the model you have, the more difficult it is to actually go through some sort of optimization to calibrate parameters. So if you are not able to do this well, the parameter you calibrated may not really be that meaningful. And then because the option price depends on the effectiveness of the calibration, if you have a parameter that are not really well calibrated, your option prices may not really be quite correct. So there are pros and cons of using a more complex model, because sometimes obviously more complex model will give you more features and something that's more pleasing that you handled the structure that's more consistent with the market observation. But on the other hand, a more complex model may be much more difficult to implement and to calibrate parameters. And if that is not done well, then the complex models may not actually give you more accurate option prices. So modeling choices is never really an easy task. So and a lot of time, the appropriateness of the model really depends on what you try to achieve and whether you can have a quality numerical process to allow you to achieve what you need to achieve here. Okay. So there's a lot of pros and cons. You have to weigh the different conflicting demands for that.